To generate electricity, we usually rely on a remarkably simple physical process: heating water into steam to spin a turbine. Conventional power stations accomplish this by burning enormous amounts of coal, natural gas, or heavy fuel oil. Even nuclear plants achieve the exact same result. They rely on the controlled fission of uranium to produce the intense heat required to boil that water. But there is a much more direct path. Deep within our planet, the core holds an immense reservoir of thermal energy, kept continually hot by ongoing chemical and radioactive processes. This internal heat gradually migrates upward through the rock layers, eventually breaking the surface naturally as hot springs or violently erupting geysers. Humanity expends massive amounts of capital and resources manufacturing heat artificially, while an inexhaustible, uncombustible thermal reservoir radiates continuously right beneath our feet. People recognized this natural potential early on. Back in 1817, the French Count François de Lardurel figured out how to collect surface steam to drive early mechanical engines. The leap to generating electricity came in 1904. The Italian entrepreneur Piero Gennaro Conti attached a generator directly to a geothermal vent. It produced just enough current to light 4 bulbs. By 1911, that initial test site in the town of Lardurello had expanded into the world's first formal geothermal power station. For decades, Italy remained the only nation exploiting this resource on an industrial scale, joined eventually by Japan in the 1920s. What began as a modest 4-bulb demonstration quickly evolved into a highly exclusive, geographically locked industrial advantage. Today, the International Energy Agency divides geothermal sources into 5 distinct categories. Each is defined by the physical form the thermal energy takes when it hits the surface. The most straightforward method is the dry steam system. Here, pure steam rises directly from underground reservoirs, gets captured by drilled wells, and is channeled straight into turbines. The most famous example is the Geysers complex in Northern California. With an installed capacity exceeding 1,500 megawatts, it is the most powerful geothermal facility in the world. The second category is the vapor-dominated hydrothermal system. In this setup, steam emerges mixed with liquid water, which means operators have to use dedicated separator vessels to isolate the dry steam before it reaches the turbine. The third category covers liquid-dominated systems, where only hot water, rather than ready-to-use steam, flows up from the subterranean reservoirs. All 3 of these direct methods rely entirely on geological luck, finding a natural combination of heat, permeable rock, and water occurring in exactly the same location. When nature provides the heat but omits the water, engineers have to intervene. This brings us to the 4th classification: petrothermal, or hot dry rock systems. To extract heat from dry rock, engineers drill deep wells and pump water down at extremely high pressure. This technique, called hydraulic fracturing, cracks the deep bedrock to create artificial cavities where the water can absorb the heat before returning to the surface as steam. The 5th category is the most extreme, extracting energy directly from molten magma burning at over 1,300 degrees Celsius. However, managing that kind of intense destructive heat remains highly experimental and is not yet deployed commercially. For sources where the water temperature is too low to produce steam directly, plants use the binary cycle method. They draw the warm underground water and pass it through a heat exchanger alongside a secondary working fluid. This secondary fluid has a much lower boiling point than water. It vaporizes instantly to drive the turbine. Because the entire loop is closed and the geothermal water never touches the turbine, this method keeps chemical emissions fully contained. It is a striking technological irony. To harness the Earth's seemingly free, natural energy, we have to design increasingly complex and resource-intensive mechanical workarounds. Geothermal power plants carry distinct advantages. They offer an indefinite, renewable timeline, they produce zero combustion-related emissions, and they provide a highly stable baseline of continuous power. But there is a steep chemical cost to pulling matter from deep underground. The extracted steam brings up hazardous compounds like hydrogen sulfide, methane, and radon. These gases require aggressive filtration and must be meticulously injected back into the earth to prevent drinking water contamination. The subterranean environment is also highly corrosive. Over time, continuous silting and aggressive mineral scaling build up inside the equipment, choking the flow and causing older wells to rapidly lose productivity. Furthermore, individual wells do not deliver steam at a constant pressure. their output fluctuates cyclically, forcing operators to constantly drill brand new wells just to keep generation levels stable for the grid. Operating these facilities requires a state of continuous mechanical warfare against the Earth's hostile chemistry. The absolute limit on this technology is geography. Geothermal viability is strictly dictated by the planet's active tectonic fault lines and volcanic zones, and exploiting these specific fault zones carries inherent risks. Scientists track a documented correlation between intensive deep well drilling and subsequent localized seismic activity. This geographic lottery creates stark global contrasts. The United States leads the world with 3,000 megawatts of capacity, yet that represents barely 0.3% of the American grid. Meanwhile, Kenya uses the remarkable geology of the East African Rift Valley to generate 51% of its entire national electricity supply. Global development continues to grow at a measured pace, with scientific projections estimating total worldwide capacity could reach between 40 and 70 gigawatts by 2030. Every single year, 100 billion megawatt-hours of thermal energy flow from the Earth's interior to its surface. It is a staggering reservoir of power, permanently locked behind a geological lottery we are only just beginning to decode.